exist in F theory, fluxes which influence the physics on seven branes. So the question is, how do you leave these fluxes to the resolutions? If you really try to leave them up, you find out that the resolution can never be Crepin. So the resolution will not be Calabian. But then you run into trouble. I mean, what do you mean by F theory on a non-Calabian manifold? And this is, of course, the famous issue of neglecting back reaction from fluxes. You have actually neglected back reaction. So you have to go back to square one. Back to basics. How did we define F theory? Well, Waffa started with this elliptically fibered manifold, okay, type 2B with the Elton axion, but of course he couldn't say anything about exactly this loci. So if you want to understand better what happens at those loci, you have to interpret F theories as a certain limit of M theory, a decompactification limit. So you consider M theory compactified on an 8 manifold. And you assume that that 8 manifold has some sort of T2 fibration. It's not an isometric vibration by any means. Okay. So this 8 manifold and 8 over some 6-dimensional base. And if you look at some fiber, let's say you pick a basis of 1 cycles on these two torus. So let's call the radii RA and RB associated to 2 cycles. That would be RB. Okay. You can think that, okay, I have M theory first in some sort of adiabatic limit when the basis is large. At least you can think that you first compactify M theory on T2. Okay, and then you adiabatically fibered over B6. And if one of these radii is small, so for example, if RA is small, then M theory on T2 is typed away on a circle of radius proportional to B. But then you can do a T-duality. So you get type 2B on a circle of radius proportional to 1 over RB, alpha prime over RB, or whatever, in whatever unit you want to be. So you see that if you want these fibers to be small, okay, you need to have one of the cycles of the dual torus to become very large. So that's the decompactification limit. And in that decompactification limit, the T2 fibers here will have area going to 0. But the dual T2 fibers, okay, you need a duality on one of the cycles, have area going to infinity, and they decompactify to circles. S1 of something proportional to RA. So that becomes an S1 fibration, which is sorry, not on an 8 manifold. I should study with a 9 manifold, excuse me. Okay, because I want an 8 manifold there. B7, which is an 8 manifold. Okay. So here I compactified from 11 dimensions in M theory down to 3 dimensions. I know, I'm sorry. It's an 8 manifold everywhere. I'm sorry. Okay, forget that. Okay, it's another n manifold, but times this very largest one. Okay? Which in the decompactification limit becomes something like an R1. So here you have type 2B. So in this limit, you see that M theory on M8 becomes type 2B. So the space here is R1 3, cross M8, communication to R12. Okay, type to be compactified on R1 free cross some M8 dual. Okay? And if you take this communication to be quite general, that will be an F-theory communication of type 2B. So that's the M-theory interpretation of F-theory. Okay? Now, why should this be good? Well, because in M-theory, we have all fluxes. Okay? So even in the supergravity limit, we know all fluxes. In particular, we know this G flux, which is the field strength of the supergravity 3 form. So if you could do this in full generality and trace through the argument, you would obtain the full story of fluxes theory. That's motivation. Okay? Now, so what does general mean here? If you look back to everything that was done in the 90s and everything, absolutely everything that people did until today, general means actually not general at all. And people think that they know this, but I should stress it's actually not true what people think that they know. So what is known about the theory on n-manifolds? So the n8 manifold, let's call it M8 or M. Okay? Well, you want to compactify from 11 dimensions to 3 dimensions. The most general thing that you can take in 3 dimensions if you want to preserve a maximally symmetric solution of 3-dimensional gravity is an ADS space with some cosmological constant which I will call -8 kappa square. So it's parameterized by kappa. When kappa tends to 0, so kappa is some positive real number, then ADS kappa recovers the Minkowski space in 3-dimensional Minkowski space. So you could take ADS compactifications, and in that way you include that. Okay? You cannot have de Sitter compactifications, of course, because of the no-go theorem of Maldacena and Nunez. Okay? So what is known? How much supersymmetry do you want to preserve? If you want to preserve n equal 2 supersymmetry in 3 dimensions, which by this decompactification would correspond to n equal 1 supersymmetry in 4 dimensions, okay? This is what we want, because we want F theory in the end. Then, in fact, the only thing that's been known until now, yes?
Sorry, I thought that Nunez and Maldacena didn't stay in the Minkowski space.
Yeah. Yeah, it says that in the case of Minkowski space, space, unless you include quantum corrections, you will need orientifolds. Because you need to, the flux has nowhere to go, okay? So here you will need to include quantum corrections, but that's exactly what we will have because we start with M theory. So M theory is not quite 11 dimensional supergravity, but something. Plus quantum corrections. So it's the quantum corrections that will solve the problem in the Minkowski space. And that's exactly what happens in ordinary F theory, of course. You need to include at least some subleading corrections to M theory, and we know at least some of them because of anomaly arguments due to width. Yeah. Okay. So in this case, all that's known is ancient. It's from Becker and Becker in 96. And they did the following thing. They realized n equal to supersymmetry in 3 dimensions with a computation of M theory on an A manifold, considering that the generators of the supersymmetry transformations are Majorana-Weil. Which correspond to Majorana-Weil spinors over the compactification space. So there's certain ansatz for, you will see in a moment. So these are the generators of supersymmetry, the internal part of the generators of supersymmetry transformations, which are spinors of spin 1/2 on M8, okay? And in 8 dimensions, you can impose the reality condition, the Majorana condition, but you don't need to impose the Weil condition. They impose a while condition simply for technical reasons. And of course, they were aware of that if you read their original papers. And this is completely not needed. Only used to simplify computations. And if you do this, you find that M8 is a Calabi-Yau fourfold. Okay? And the internal part of the G-flux is a primitive four-form on this Calabi-Yau fourfold, which is, of course, a celebrated result well known. And this is, in fact, what you use as a starting point when you want to interpret classical F-theory as a limit, the decomplication limit of F-theory. So if you do of M-theory, if you do the decomplication limit here, you get F-theory on, you have to impose the condition that you have a T2 fibration on elliptically fibered fourfolds, Calabi-Yau fourfolds, which is what I call classical Buffer-Morrison theory. Oh, so now we are in business. Aha, we went back to square one, and we understand why people, when they try to make sense of fluxes and they try to resolve, they're stuck with the problem of finding something that cannot be Calabi-Yau. It comes back from this assumption. So now the road is clear. You have to remove that assumption. And shockingly, nobody has done it. How many years since then? Okay. Never has anyone removed the purely technical assumption, the unneeded assumption, while condition on the spinors, on the generators of the supersymmetric transformations. So that was the motivation of all of this. So you now have to remove this assumption. So study in true generality the most general n equal to compactifications of M theory on 8 manifolds with n equal to in 2 dimensions, and then take that limit. So it's quite obvious that you should be able, because the existence of a T2 fibration has nothing to do with supersymmetry. You should be able to do this, so you should be able to generalize F theory. And hopefully explain why they got non-crappant resolutions if they wanted to explain G fluxes. And that's how we got started in this. Okay. So this is the motivation. Now, what happens if you remove that innocuous-looking while condition? It looks like, okay, it should be easy. My first attitude was, okay, that really shouldn't be much harder than Becker-Becker. But of course, Becker and Becker are very good, so they had a very good reason to impose that condition. It turns out that if you remove the while condition, all hell breaks loose. Okay? So take Xi1, Xi2 to be just Majorana. So there are sections over this M8 of the bundle of real spinors. So Majorana spinors in 8 Euclidean dimensions, because it's in the internal directions. So it's a rank 16 real vector bundle. So vector bundle with fibers are vector spaces over the reals of dimension 16. The bundle of Majorana spinors. And there are global sections over M8. And then turn the crank. So redo the compactification ansatz. And the first thing you'd like to do is to understand the geometry, so that you know how to take the limits, the F theory limit. It's unbelievably hard. To see just how hard it is, let me rely on those, because I don't have time to write, rely on showing you some formulas. So how does it go? So you have this gravitino in 11 dimensions supergravity. You take a supersymmetry variation in 11 dimensions. This hats means that I'm in 11 dimensions. So eta hat is this Majorana spinor in 11 dimensions of spin 1/2, which is the generator of the supersymmetry transformation there. And of course, we know that the supersymmetry variation of the gravitino is given by the covariant derivative of the supersymmetry parameter with respect to the supercovariant connection, celebrated supercovariant connection of 11 dimensions supergravity. So we need to require vanishing of this supercovariant derivative of the generator eta hat. So you can see this, how this looks. It has this pretty ugly form in terms of gamma matrices in 11 dimensions. Then you, of course, if you want to include ideal spaces, you need to put a warp factor. So it's not just a direct product, a metric direct product, but you have some warp factor. So I wrote it here as being conformally equivalent to a direct product, because the warp product is always conformally equivalent to a direct product. The warp factor is delta. You separate into 3 and 8 dimensions. This is the ansatz for the flux. So the 4-form flux with this decomposition will induce a 4-form on the internal space, which, because of summary scaling, is by delta, I denoted by F, big F, rather than G. And the 1 form, because there's this piece, which is the volume of the ADS3 space wedged with the 1 form. Okay? And of course, you have a similar decomposition for the spinors up to summary scaling by the warp factor. The spinors are essentially a tensor product of what lives on the external space and what lives on the internal space. And after you turn on the crank, how the equations decompose, you find that this supersymmetry condition in 11 dimensions amounts to 2 conditions on the internal part of eta, which I will call psi. Namely, you need to impose an algebraic constraint on psi. So there's this Q here. You need to require that psi lies in the kernel of Q. So Q is a section of the bundle of endomorphisms of this Majorana spinor bundle over M8. And the psi is flat with respect to some induced connection on that bundle of Majorana spinors, which has this particular form where nabla MS is the spin connection. Okay? So that's the decomposition. Whatever. So I went through all of this. Yes?
So the ansatz for eta,
Yes.
you take it as a product?
I rescaled it already. I had an eta hat. I had an eta hat here. There's an E2 delta over 2 times eta, and eta is a product. So, yeah. This is completely generic. So what will happen is that I require that there are 2 solutions psi for these equations. So I can require to have 1 solution, 2 solutions, 3 solutions, and then I will preserve n equal 1, n equal 2, n equal 3 in 3 dimensions. And that's actually what always happens in supergravity communications. You can simply have a space of solutions for these internal equations, which is smaller or larger. So the equations are these. These ones. The algebraic constraint and the differential constraints, which is a condition of generalized flatness with respect to this weird connection of the spinor bundle, Majorana spinor bundle. And the question is how many solutions are here. If you have 1 solution, you preserve n equal 1 supersymmetry in 3 dimensions. If you have 2, you preserve 2 supersymmetries. So you have to analyze this system. And of course, this system is formulated in terms of gamma matrices and spinors, so you don't like that. It's not very geometric. It's not so easy to put your hands on spinors. So you'd like to translate it into a system of equations, namely algebraic equations and differential equations for spinor bilinears, because everybody knows since childhood that if I give you a bispinor, so in essentially 2 spinors, I can form spinor bilinears. So if I have 2 solutions, if I have psi 2, I can form okay, essentially this. Yeah. If you want There's a bilinear spin invariant form on the spin boundary, etc., which I call B, which in this case turns out to be a scalar product. So, okay, and if I call this eta mu1 mu k, xi1 xi2, that gives me a form. The spinor bilinears give you forms, so you should be able to translate all those equations into equations for spinor bilinears. The translation back is very subtle. It comes because there is something that I call the Firth isomorphism, E check. But it's sort of premature at this point. And because this is an isomorphism between a certain subalgebra, in the case of M8, it's an isomorphism between the algebra differential forms of on M8 and the bispinor algebra, which is isomorphic with the endomorphism, the algebra of sections of the endomorphism bundle with the composition. Okay, this I wrote it here as an isomorphism of vector bundles. That's the exterior bundle of M8, okay, because I don't want to put the sections. So because it's an isomorphism, you can actually pull back. But okay, even this is new. The concept of Firth isomorphism is new. I introduced it. Nobody has a systematic way to do this. I mean, until now, nobody has a systematic way to go back. Okay. So you like to do this. And of course, you are going to run through a very large number of technical problems, because everybody knows that if you have spinor bilinears, which is what these forms will be, then in between two spinor bilinears, you get, if you take their product, you have a combination with 4 spinors, and of course, you have Firth identities. So they will not be independent. So these forms, omega k, which I just constructed, are not algebraically independent due to Firth identities. So there will be an awful lot of Firth identities with omega k, omega l. You can consider any sort of combination of wedge products, contractions, etc., many, many operations, and this will give you back linear combination of these forms. So it's horrendously complicated, because how in the world are you going to write down all possible combinations of wedge products and contractions between the spinor bilinears and write out all possible combinations of Firth identities? There is an algebra called the Firth algebra, given by all these constraints. And the first question is what it is. What is it? Okay. How to characterize it. And if you try to do it by hand, it's just awful, because awfully many Firth identities, and you have no systematic approach known in the literature, exists in the literature. Firth identities, for those who study supergravity, are the bane of supergravity. Every supergravity theory can be reduced to some Firth identity. That's why it's actually supersymmetric. And they are the reason why supergravity is very hard. So you have that problem. Second problem you have is you have to actually translate these equations into equations on the bilinears, and you would like to have a systematic method. And if you check through the literature, the closest to something systematic can be found in a paper of Marteni and Sparks in 2001, where they studied n=1 compactifications in the same setup of M theory. And it was already quite horrendous. And it's not at all clear that you can make it work in this case. In fact, we tried, and it's very, very complicated with code, with cadabra, with all sorts of things. It's just a mess. Also a mess. And it turns out that if you do impose the while condition, this mess simplifies drastically. And that is exactly why Becker and Becker did it. Good. So are we to give up? And my answer is no. I have an idea. And the idea is quite sophisticated and technical, and turns out to lead to way, way, way more applications than just this particular case. In fact, I think that you can rewrite all of the theory of flux communications and make sense out of it, systematize it, and you can systematize a very large part of supergravity and of string theory. For example, issues of effective actions and so on in string theory by using it. And for some reason, even though now it seems quite obvious to me, it was never used in supergravity. And the idea goes by the name of geometric algebra. So if you go to Google after this talk, if you type geometric algebra, you find also lots of references, even a Wikipedia page. So you might think, oh my God, I mean, why didn't anybody notice this? Well, there's a number of reasons. There's a guy called David Hastenes who played with geometric algebra, but for some reason, he only considered it in 3 and 4 dimensions, and he only applied it to classical mechanics, and a little bit of the Dirac equation in 4 dimensions in Minkowskian signature. So there's a beautiful theory, but he never developed it in general, because we want other dimensions and signatures. And he has no really hard applications. And I think the secret of the reason is that he doesn't know supergravity, because if you know supergravity and geometric algebra, it's quite obvious that this approach has to shine in supergravity. Okay? So you need to do it properly, so do it generally. So arbitrary dimensions and signatures, if you want to make it ready for supergravity. You won't find this on the web. Very few references even come close. Okay, and then develop some specialized branches, some specialized applications. In particular, formulation of Firth identities, and that's going to be the answer to that mess. And what I call the theory of constrained generalized killing forms, which is really the theory of forms satisfying algebraic and differential constraints of the type that you want for the spinor bilinear, and how to translate between spinors, between constrained generalized killing spinors satisfying algebraic and differential constraints, and constrained generalized killing forms. And of course, there's a well-known, very classical notion of killing forms and killing Yano forms and so on. And this will provide a very interesting generalization of that. In particular, generalize the classical theory of killing Yano forms by considering systems of forms satisfying a coupled differential and algebraic equations. So it's very, very much more general. But not quite any system, but a system constructed for something called the diamond product. So it's a very special thing. So in a very interesting way, I think. And because these are differential systems on forms, you have some relation to covariant Keller-Cartan theory, the theory of differential systems of PDEs formulated invariantly on manifolds. So you get into some pretty serious mathematics. Okay? Yeah.
There is some hope with the kind of
Yeah.
a way of classifying supersymmetric compactification in terms of holonomy.
Yeah. G structures.
Generalizing the holonomy from Riemannian to non-Riemannian.
Absolutely. And I will say about,
Relating to that?
yeah, that's my next point. And you will see just how subtle even that is in this case. That's exactly my next point. What about G structure classifications and holonomy of generalized connections and so on and so forth? So this connection is some sort of version of a generalized connection, but not in 11 dimensions, but on your internal manifold. And it has a certain holonomy. And let me tell you about this. So this DM is a connection on this Majorana spinor bundle on S. It turns out that S has a scalar product, because the spin invariant bilinear form in 8 Euclidean dimensions is actually positive, definite, and symmetric. And if you look at the connection and you actually take transpose, you see that DM is of the type spin connection plus some AM, where this is that particular combination of gamma matrices, and this AM is antisymmetric, which means that this connection DM preserves this bilinear form in the sense that for any two spinors xi prime, you have this relation, which is a very crucial observation which doesn't seem to have been made before, because nobody thought in terms of these connections. People actually write equations in components, so they didn't actually think in terms of connections. So it's just this condition, because everybody knows that the spin connection, that B is flat with respect to the spin connection. So that is satisfied by B, and then anti-symmetry implies that. Okay, so what this means, of course, is that the parallel transport of dm, okay, is realized through orthogonal operators which preserve this product. So if you have the fibrous x at some point x and at some point y on M8, this parallel transport u xy for some gamma, right? You have to choose a path because it might be in a non-simply connected case, so it might depend on the path. And this connection is not flat. Okay, B is flat with respect to it, but the connection is not flat. It has curvature. Okay, but the parallel transport on gamma will have the property that u gamma psi prime, the B product of u gamma psi and u gamma psi prime, is the B product psi prime for any psi prime in the fiber at x. So the parallel transport is realized through operators which are orthogonal with respect to the scalar product B. So that is the holonomy. So that means, of course, in particular, the reduced holonomy as well as the full holonomy at a point x is a subgroup of SO16, because 16 is the rank of my bundle, and it's a real vector bundle. So that is all you know a priori. But you have this inclusion. So it's not GL of 16R because of this. So it's not like this, the supercovariant correction in 11-dimensional supergravity for an arbitrary background has no such reduction. But there is such a reduction for compactifications of this type with this ansatz for the fluxes and the metric, this word product ansatz. Then there is a reduction for the internal part. So that's the answer. But there's, of course, a lot more than you can say. And there's a lot of mathematics that you can discuss here, but I won't go through the details. You want to have two spinors. And, of course, you want these two spinors to satisfy some constraints. But because there's this holonomy, and because one of the equations tells you that these spinors are flat with respect to this connection, this means that their values at some point y are related by parallel transports on some curve gamma between x and y to their values at x. So in particular, any linear dependence relation that holds between their values at x also holds between their values at y, and conversely. If they are linearly independent at a point, they will be at any point. So in fact, clearly, because of this, the dimension, and that answers the question that Julia put to me a few days ago, of the space spanned by two solutions is independent of x. Spanned by the local values of two solutions at some point is independent of x. So if you have two linearly independent solutions, they have to be linearly independent not just as sections, but their values at every point, which are just vectors in the fiber of x, have to be linearly independent at every point. So the dimension of this space has to be 2 in our application. This is just a trivial application of the notion of holonomy, right? Parallel transfer. Good. Now, you have that, but one of the things that you have when you have two solutions, you have these spinors which are linearly independent everywhere, and they also have to satisfy those properties. Just from the fact that you have two spinors which are linearly independent everywhere, they are everywhere. Everywhere means the local values at every point are linearly independent. You might hope to be able to build a reduction of the structure group of M8. It turns out that there is no reduction structure group of M8 because the spinors are not vial. But there is the reduction of the structure group of the metric cone over M8. which I will call M9, has a reduction structure group. Well, M9, of course, has, if M is oriented, then it's going to have SO9, but in general it has O9 as a structure group, because it's a Riemannian manifold, so structure group of Riemannian manifold is O9. And the reduction is to G2. And in fact, there's an equivalence, and this is a theorem. However, one moment, the structure group of M8, which is O8, does not generally reduce to any subgroup unless the spinors are both Weil. To any subgroup. If gamma 9 xi1 is plus minus xi1, well, epsilon 1, some sign factors, if they are both Weil of whatever chiral it is, then SO8 does reduce to SU4, which is the Calabi-Yau case. And that's why, a lot of people think that you always have to have a reduction structure group if you have some supersymmetry, if you have some globally defined spinors. It's simply not true. The reduction structure group, if you go through a mathematical theory, happens only if the structure group of the tangent bundle of your Riemannian manifold acts, the spin group which covers the structure group of the tangent bundle acts transitively on the collection of spinors under consideration. And it turns out that the reason why this is not true is that spin 8, which is the double cover of SO8, does not act transitively on two independent spinors in the fiber. What are two linearly independent spinors in a 16-dimensional space? Well, two vectors in a 16-dimensional space, if they are linearly independent, they form a point in the second Stiefel variety of the space. But spin 9 does act transitively. And that's why this phenomenon happens. Of course, it's not just that. You have to go through the classification of transitive actions of spin groups in various dimensions. And that actually is some heavy math. And I found it in a Habilitationsschrift of some German mathematicians. Written in 2006. So it's actually not at all trivial to prove it rigorously. Yes?
What was M9?
M9 is a metric cone. Metric cone over M8. Let me remind you what it is. So M9, because I want a manifold, I take out the apex of the cone. So it's diffeomorphically just 0 plus infinity tensor R, which up to tensor M8, which up to diffeomorphism, you can take the exponential function here to give a diffeomorphism between 0 plus infinity and the real axis, is diffeomorphic to the cone, to the cylinder over M8. So that's diffeomorphic. But it's not isometric, because metric is given by that's a line element squared over M8. Okay? While for the cylinder, it would be du square plus ds8 square. And of course, the cylinder, the cone are conformally equivalent, the conformal transformation being given by u is log r. They are conformally equivalent as Riemannian manifolds. So M9 with this metric G9 is conformally equivalent to the cylinder with this metric G cylinder 9. Okay? That's just trivial. Okay? Good. So This is the story. In fact, the structure group of the cylinder also reduces because structure group is a conformal invariant. So I prefer the formulation of the cone because that's actually better from a number of points of view. So this tells you something about structure groups. So this is one of those famous examples in which a structure group doesn't reduce even though you have spinors which are linearly independent everywhere. And it might come as a surprise to some people because there are even reviews in the literature which claim the structure group always reduces. And that's simply patently wrong. There were previous examples of this type. This famous paper of Martelli and Sparks. They looked at the most general n equal 1 compactification to d equals 3, the same ansatz in 8 dimensions on M8. All the formulas for the connection, etc., are the same, but they want a single spinor, which is Majorana. And in that case also, the structure group doesn't reduce. And it was shown by Tsimpis that the structure group of the cylinder, which is the same as the structure group of the cone, reduces to spin 7. But structure group of M8 does not reduce. So that's been known since then. That's why it's surprising that reviews written in 2007 claim that the structure group always reduces. But they don't quote Tsimpis. So this is Martelli and Sparks, and this is due to Tsimpis. 2004, I think. Yeah. So it shouldn't be surprising the structure group does not always reduce. It's simply patently wrong. It happens in certain cases, but it doesn't always happen. And there's no mathematical reason to happen unless the spin group of your manifold that's transitively on whatever collection of spinors you want to have. And transitivity is a very subtle issue, and it doesn't always happen. In fact, it's heavy math. And there are many unsolved issues about transitive actions of spin groups. For example, for the third Stiefel manifold of R16, nobody knows if the action of spin 9 is transitive or not. Still an open question. So attention. Things are not so easy. Good. So that says a little bit about G structure. So of course, in principle, now we are in business. You could do two things. First, you could do the general theory of G structures of 9-dimensional cones. Okay, G2 structures on a 9 manifold. These have never been classified. There is no great Hernandez-like classification of intrinsic torsion for G2 structures in 9 dimensions. They only did it in 7 dimensions. And also there is no such classification for spin 7 structures in 9 dimensions. It was only done in 8 dimensions. So you could try to do that and do such a classification. Of course, it's going to be very complicated because it's a deep reduction structure group. G2 sits inside an SO8 subgroup of SO9. So the deeper the reduction, the more cases. So it's going to be heavy, and you're going to have to do it with code. Even the original Gray Fernandez and so on was done with code, with Maple and so on. And sorry, at that time they didn't have Maple. The first papers, I think, this, I don't, whatever existed before Maple. Okay. They had these other symbolic systems. Okay. So you could do that, but then of course that only gives you some classification. The intrinsic torsion coefficients have to be specified by those equations, the d-flatness and the algebraic and these constraints, the differential constraint and the algebraic constraint. So it will be what you need in physics applications are very particular subclasses of these Gray-Hernandez-like classes that you would find. Okay? So let's see exactly how particular. So how do we solve the remaining problems? Well, we can, using this geometric algebra formalism. And I was telling you that I want to impress you with how horrible it is. So after you use this geometric algebra formalism, you can write these equations in a funky way, which looks much better than they would look otherwise. So index-free and all that. What you do, you introduce what I call the dequantized connection, which is actually a connection valued in the Keller-Atiyah bundle. So essentially, it's a one form valued in the exterior bundle, in the bundle of inhomogeneous forms, which is a very weird thing, but it's actually very useful. And some sort of dequantization of Q. It's a geometric quantization. They look like this, expressed in terms of the word product and whatever, so index-free. And you turn the crank of this theory of geometric algebra, you find that a set of algebraically, linearly independent bilinears given by this, because essentially all the others vanish. So, so you have 3-1 forms, 1-2 form, 1-3 form, and 3-4 forms on this space M8. Constructed as spinor bilinears in this Xi1 and Xi2. Okay? And there's this killing algebra that comes from this development of geometric algebra theory that I did, which turns out to be isomorphic to an algebra of 2x2 matrices with real entries. So it's so easy to actually classify algebraically that field algebra is just mat to R, which is spanned, for example, by the Pauli matrices. Turns out that you have a very simple answer to that if you go through all this geometric algebra development. So you can choose generators in a number of ways. You can choose E12 and E21 as generators. And you use something called the generalized product, so these little funny delta k's. A delta k expands like this. We wrote a lot of code and procedures. This is an example of delta k, so you can see just how ugly it would be if you were to do it by hand. This is another example of a simple delta k, delta 1. Okay? And you end up with equations written like this in terms of star product, that's a Hodge dual in 8 dimensions, and generalized products, delta 3, delta 1, whatever, and wedge products. Okay, so these are the algebraic constraints. These are the differential constraints, all of them. This is complete, absolutely complete. We haven't done no cheating. And we have also complete characterization of the generators. And these are the field identities, all of them. This, what these red arrows show are that some of those identities are dual to others. They're equivalent to the others by applying something called reversion, which is an operation in geometric algebra. And the bullets show that the corresponding equation is self-dual via under reversion. So you have 16 equations, but they're not all independent. There are only 10 independent. And of course, each of them has many rank components. These are written in terms of inhomogeneous forms. So when you expand them, you actually hit this enormous system of equation written, which is still very ugly, even though it was written in terms of the generalized products, which come from geometric algebra. But we did find the independent ones, and we actually solved this system. And that's part of the second paper in this series that we are writing. You can actually solve it also through these geometric algebra techniques. So you can actually give a complete translation of all these equations which makes connection with non-commutative algebra. So geometric algebra shows that all of these things are in fact equivalent to problems in non-commutative algebra. So in the future, in such problems, you could use more sophisticated code. Something like plural. Yeah, Lewandowski's extension of singular to non-commutative algebraic geometry. It becomes a problem in non-commutative algebraic geometry, really, which is quite surprising. Because nobody thought before that such problems can be solved by using techniques of non-commutative algebraic geometry, but this is actually what it becomes. Okay? Now, our implementation was in 2 pieces of, actually 3. There's some package for Mathematica called Grassmann algebra. We have an implementation there. Some package called Ricci. And of course, in Cadabra. So these are Mathematica packages. Trademark. Okay, good. So we have implementation, and there's a lot of coding to be done. Now, of course, what I didn't yet tell you anything, I don't know if I have any time left, is what is this geometric algebra and what it does for you. So that's, of course, I have a paper that's going to come out soon, the first in this series, which is already 80 pages. So it's going to be like, 10 minutes. So what is this technology of geometric algebra? Let me say a few words and what it does for you. So how do you actually go by solving this problem, understanding the geometry? solving all these computational issues which are horrendous on the face of them. Why Becker and Becker didn't even think of trying. Okay, so there's something called spin geometry. So there's even a book by this name, a famous book of Blaine Lawson and Louise Marie Michelson. So Lawson and Michelson. And its old stuff is from the early 90s. And what is this really? It's a theory of spinors in curved spacetimes. So theory of spinors. The correct, proper mathematical theory of spinors on arbitrary pseudo-Riemannian manifolds. So in particular, Minkowski and Euclidean qualify. And it's a theory that almost everybody uses, and the approach is due to Cartan. The approach is through spin structures. So you take this pseudo-Riemannian manifold MG. Okay, it has a structure group. Consider the group of pseudo-orthonormal frames. It has the structure group SOD signature of D, yeah, PQ. So suppose that the metric has signature type PQ. So P positive eigenvalues, Q negative eigenvalues. So you can consider this as a structure group. It has a spin cover. And of course, if you don't have an oriented manifold, you also have pin covers. So let me just write them here. So pin C, pin, spin, SOPQ. Inside there, the spin C. And above everybody is the smallest, the largest group you can have, which is called the Clifford group of the Lipschitz group C. C means a U1 extension. Okay. So you start with any of these refinements of the principal bundle with structure group as the principal bundle of orthonormal frames. So let's call G any of these. GS from spin. Okay, and you can consider an associated vector bundle, which you call the spinor bundle. So from here into the endomorphism bundle and the spinor bundle, you are going to have a morphism into the units of the endomorphism bundle. So you preserve the product here, goes into composition of operators there. Okay, so E is associated to GS by some representation of the spin group on some representation space. Any of the fibers will be a representation space. Okay? So it's a bundle of spinors. And then you turn a crank and so on and so forth. Okay? Good. Now, it turns out that you can do better. Okay? This is the approach due to Cartan. The problem with this approach is that there are many, many choices. So everything is determined actually only up to isomorphism. In all of these covers, everything is determined up to isomorphism at a point. So when you globalize, you take the point to move over your manifold, everything will depend up to isomorphism of bundles. So things are determined only up to isomorphism. And because of this, you actually lose some very important information. And the idea of geometric algebra is to change track and use a specific, very specific, but very intelligent realization of all of these bundles. So in this isomorphism class, which is typical of spin geometry, everything is determined up to isomorphism of bundles. You will take precise special representatives of stuff. And those special representatives allow you to mix the theory of spinors and the theory of differential forms in a very useful way, okay, which in particular allows you to perform very heavy computation to understand things better. So what's the basic point? You start with the Clifford bundle of the cotangent bundle to M. So if there's a metric on M, the metric is a bilinear form on the tangent bundle. That induces, by raising indices, a bilinear form on the cotangent bundle. So you can take the Clifford bundle. What does this mean? Every cotangent space with G hat, which is, or G minus 1 if you want, the metric induced by G, is a quadratic space. So you can take the Clifford algebra of that quadratic space, and then you fiber it over M. So you get a bundle of Clifford algebras. That's called the Clifford bundle of the cotangent bundle. And the idea of geometric algebra is to realize this Clifford bundle as the bundle of differential forms in which the Clifford product, right, Clifford algebras are associative but non-commutative, is realized as a product on the fibers of the exterior bundle. So identify as vector bundles, in the category of vector bundles, with the exterior bundle. So this is the direct sum of all of the pieces of definite ranks. These are the bundle of K forms. D is the dimension of M. And when you do this identification, this Clifford multiplication here can be, because this is an isomorphism bundle, can be transported back to an associative but non-commutative multiplication, which I denote by diamond, on the exterior bundle. So in fact, in this way, you make the exterior bundle into a bundle of associative but non-commutative algebras. Of course, on the exterior bundle, you also have the wedge product. You also have contractions. You also have all sorts of combinations of wedge products and contractions, which involve raising and lowering of indices and whatnot. And you have this operation. So you might hope that there's a realization of this isomorphism, which allows you to elegantly express this diamond product in terms of contracted wedge products. And in fact, it is true. And the simplest way to understand this is to do a little bit of geometric quantization. So you can think of this as a space of functions over a supermanifold, which is called pi Tm. So you simply take the manifold M, you take the tangent bundle, and you change the parity of every fiber. Okay, so you view the fibers as being odd. So then dxi are identified with coordinates zeta I, which are odd and anti-commuting Grassmann coordinates on the fibers. Okay, so this as a supermanifold has coordinates xi and zeta I, this pi Tm. So then a differential form is identified with a function on this supermanifold. Excuse me. It's identified with pi Tm. Okay. The function being, if it's an inhomogeneous differential form, you have components of ranks k. So instead of dx mu1 wedge dx mu k, you write zeta mu1, zeta mu k, with Einstein summations over the mu's. And you just find out, there are many ways to show this, that the diamond product can be expressed in this supermanifold language as an odd vertical variant of the Moyal product from, which is well known from deformation quantization. Here you have the left derivative with respect to these odd coordinates zeta mu. Here you have the right derivative with respect to these odd coordinates zeta nu. Here's the metric with coefficients upwards, so the inverse metric. And you act on f eta. So this is an exponential which spans in a series of bidifferential operators. The series terminates because the sums here are finite. So if you go and turn the crank, you show that this gives you an expansion of this generalized Clifford product into generalized products, which I call delta k, with some sign factors, prefactors. You can find them in the paper. These generalized products being essentially the piece of degree minus k. So if you want, you can put an h bar here, so you can rescale the metric into 1 over h bar the metric. Then the inverse metric has an h bar. So this will simply be the component of degree h bar to the k. So this is a semi-classical approximation. You can think of this as the quantum product, and these delta k's as the pieces, the h bar expansion of the quantum product. And of course, for k equals 0, you have the delta naught is the wedge product. So this realization of the Clifford bundle is called the Keller-Atiyah bundle. It's a bundle of algebras. The ideas come from Ries, the guy who was doing functional analysis, from Chevrolet, so they are quite antique, but they were very rarely used. And they were used by Keller in his theory of the Keller-Dirac equation, and by Atiyah in the 70s, and then by this Heston et al., these geometric algebra people, and some people who do robotic vision in 4 dimensions, because there the Clifford algebra, Clifford 2,10 appears. The same one that would be relevant for F-theory, but God knows why. And OK, so it's good for many things. But this is the basic idea. So these are the generalized products. And they have a recursive expression, OK, which comes from here, for example. It's very easy. So if omega eta has inhomogeneous forms, you just take I e mu of omega. E mu is some frame. OK, it doesn't even have to be orthonormal. G mu nu, I e nu of eta, and that's delta k minus 1. So you can expand it up to k equals 0, and delta naught is the wedge product. So that's what you find, which is very, very beautiful. You got rid of this product, abstract product on the Clifford bundle. You made it very, very concrete, in terms, express it in terms of iterated wedge products and contractions. So all you need to know is the metric, because you need a metric in order to do this, OK, and the wedge product. And in fact, you presented it as a deformation of the wedge product, a quantum deformation, where the quantum parameter is the inverse overall scale of the metric. So if the scale of the metric goes to infinity, hint, hint, that's the decompactification limit, then you recover, all these are suppressed by powers of the scale, inverse scale of the metric, so you recover the wedge product. So it's extraordinarily beautiful, because we always want to have this decompactification limit, right? In particular in F-theory. It's very, very nice, very nicely adapted to all of this stuff. So now, how do you describe spinors? That's an idea going back to Friedrich, a German mathematician, which some of you may know, Friedrich Agricola, all this work on flux compactifications related to relation between flux compactifications and these connections, torsion-full connections and G structures and so on. And Trautmann, who is Polish, but so spends most of his time in Berlin. Yeah, they have papers, the latest in 2007. The idea is actually quite simple. Instead of starting with spin structures and so on and so forth, you define a bundle of spinors as a bundle of modules over the Clifford bundle. By definition, just a bundle of modules. Modules means representation. So it's a vector bundle, and the fiber attacks of that vector bundle carries a representation of the fiber of the Clifford bundle, which is a Clifford algebra for every x over the Clifford bundle of T star n. Okay. So what does this mean? Well, it means S is a vector bundle over M, and we are given a morphism of algebras gamma from the Clifford bundle of T star M into the bundle of morphism of bundles of algebras. So it preserves the products. What is the natural bundle of algebra associated to S? Well, the bundle of endomorphisms, because an endomorphism is at every point just a linear operator acting in the fiber of S, so you can compose to such things fiber-wise. So that's a bundle of algebra, bundle of endomorphism, and that's with the Clifford product. But in geometric algebra, this was identified with the exterior bundle together with the diamond product, this Keller-Atiyah bundle. So in other words, a spin bundle is just a morphism of bundle of algebras from the Keller-Atiyah bundle into the bundle of endomorphisms of a vector bundle. of S, yeah? Okay, that's the gamma matrix representation. That's why I call it gamma. If you pick a coframe E mu of M, so a set of 1 forms which are linearly independent at every point, okay, locally, at every point of an open neighborhood, okay, then gammas of E mu are the gamma matrices within the X upper. So they are endomorphism sections over U, so a coframe above U of the endomorphism bundles of S. So at every point they are just linear operators in a finite dimensional vector space, so they can think of them as matrices, but the matrices depend on the point. Beautiful. And Trautmann and Friedrich, they also have a paper before that, I think in 2005. They show that this is equivalent to the approach through spin, pin structures, all of that, that nasty sausage, due to Cartan. So the theorem says that the most general thing that you can do, namely the pin C structure, the Clifford C structure, is equivalent to this. So S is a bundle of spinors in this sense, if and only if M admits a Clifford C structure, also known as a Lipschitz structure. The Clifford group is also known as a Lipschitz group. And S is associated to this Clifford C bundle, principal bundle of M, the Clifford C structure of M, by some representation on any fiber. Okay? So in other words, if it's a spin bundle in the most general sense of spin geometry, of Cartan. Okay? So really, generally, you don't have pin, spin, anything. The most general thing is that it turns out that a Clifford C structure, if your manifold is even, is always equivalent to a pin C structure, but when the manifold is odd, it's something more general. And I want to stress that even about this, you find a lot of nonsense in the physics literature, even people who supposedly write papers just about this. They forgot the Clifford C structure. The pin C structure is not the most general thing in odd dimensions. And of course, if you impose extra conditions, you find pin C, etc., and you find all of this in these two very beautiful papers of Trautmann and Friedrich. So it's equivalent to the theory. However, it's better than the theory because you got rid of all of those nasty isomorphisms. Everything was fuzzy. Now everything is very precise, and you very naturally mixed forms and spinors. So now this is recursive, yeah? The definition of generalized products was recursive, and the Clifford product, this diamond product, was just an expansion of generalized product. Being recursive, it's ready-made for coding. You can start coding. So now you can write procedures, and you implement this Clifford product and whatnot there. So of course now you can do a lot more. You can do a representation theory. So the representation theory of Clifford algebras globalizes to these representations of the Keller-Atiyah bundle. And you can mix this very nicely with the theory of forms. You find in particular the issues of non-faithfulness. So this gamma may fail to be surjective or injective on the fibers. So it may have a kernel, which is a space of so-called twisted anti-cell dual forms, when it's non-trivial, or it's 0 when it's trivial. That's the faithful case. And it has an image, and the image is not the full bundle of endomorphisms of S, but only this bundle of endomorphisms of S, which commutes with a certain real complex or quaternionic structure on S, given by the so-called Schur algebra of gamma. Okay, that was studied by Okubo in the late 90s, 97 or something, and by Alexeyevsky and Cortez, who are mathematicians. They were into classification by linear forms, which are spin invariant. Okay, so the Schur algebra is what? So you look at those endomorphisms which commute with the entire image of gamma, which commute with all gamma matrices. And it turns out that in general, that Schur algebra is not trivial. It's not isomorphic to R, to the real numbers, but it can also be isomorphic to the complex numbers, the algebra of complex numbers, or the algebra of quaternions. And depending on that, you will have trouble. And the image of gamma is just the set of those operators acting on S, so those elements of the bundle of endomorphisms which commute with the Schur algebra. Okay, so the Schur algebra globalizes to the Schur bundle because you have a Schur algebra at every point, but because it's a bundle, they are all isomorphic. So, okay, etc., etc., up to isomorphisms R, C, or H. Okay, good. So you go through all this, then you have to do all the cone formalism in geometric algebra and the cylinder formalism in geometric algebra, and you put them all together in a very smarty-pantsy way, and that's how you get those formulas and those things. In particular, you can formulate Firth's algebras and so on. So that's where all those computations came from.